In the following two lectures, I want to describe to you our recent paper on clustering learning, and I want to also comment and show you how the code works for such clustering learning in details. So the paper that we recently published is this one. It's called the Clustering Learning for Robotic Vision. It was just published a few weeks ago on January 2013. So what we did is we started working on clustering learning technique that are quite similar to the k-means clustering of Adam Coates, although we started quite independently just last year. And we wanted to apply them to deep network, in particular convolutional neural network. So what we did really, the focus of this work was to try to break free from the common typical practice in deep learning, which is to try to focus on a specific data set and train supervised and try to improve the technique numerically by a few percent. What we were interested more, it was a simple and supervised technique that allows you to, that is simple to implement and to understand, and allows you, has the power to learn hierarchical network, so that it can be used in a robotic vision system where, for example, you don't have a data set, or you don't want to have a specific data set to begin with, but you want to learn the data set on the fly as you progress. So I recommend you all read this Clustering Learning for Robotic Vision System and the philosophy behind it, which is really the fact that we need to break free from labeled data as much as possible, try to focus on unlabeled data, train networks that are deep and can extract features as fast as possible and as well as possible, and not focus on maybe spending a lot of time trying to beat the state of the art in one data set by a few percent, when the network and the tricks that one uses to do so do not really apply or are not easily transportable to a new data set or to a new application. So that's basically the philosophy of this paper. What we did is we used two data sets, the CFAR and the Street View House Number. It's also quite similarly to Adam Coates as well. And we trained a network that basically was composed of this module. So we had an input image. So instead of using a convolution, because we were learning k-means filter, which are basically computed by looking at the distance between a prototype and the kernel, we thought that instead of doing convolution, we should probably be doing an operation that is slightly different. We should look at sums of absolute difference, even here, or basic template matching, to try to match the features to a specific part of the image or specific patch. The difference between sums of absolute difference, or SAD, we call it special SAD module here. We use the torch package. The special SAD module has the difference that it matches very well. When it matches very well, it gives you an output of 0, and when it doesn't match very well, it gives you a large output. So it's quite the opposite of a convolution, really, in terms of output. Because it gives you a large output, after this we need some kind of a special contrasting or normalization that zeroes the data mean mostly, and reduces the standard deviation so that it can be, before we go to the nonlinearity, then we do L2 pooling as recommended by Jan LeCun over two by two regions, and then we go to a standard nonlinearity, and then we do again a spatial subtracting normalization to zero the data mean, to make sure that the output is centered in the 0. Also, all the patches and all the input images, we usually try to keep them with the 0 means. We also tested the standard convolutional neural network with the same kind of filters, or even purely supervised, with the spatial convolution, L2 pooling, hyperbolic tangent, and spatial subtracting normalization. So very similar beside this spatial set. These are the filters that we found on the first layer, and on the second layer we used basically two-layer processing, one or two-layer processing. We wanted to keep, differently from Andrew Ng and Adam Coates' work that we just discussed, we wanted to keep the number of filters as small as possible, so that the network could be run in real time on a mother processor. We used the Torch 7 package developed by Ronan Colobert and others. We wanted to be able to run this algorithm close to real time, so that even with an accelerated hardware we could boost up the network by maybe 4x or 5x, but not necessarily go to 1600 features that other groups have done that we're not really able to run in real time nowadays. So we usually use 16 filters on the first layer and 64 on the second layer. And all these filters, by the way, they're trained with the clustering learning technique. I'll describe the code in a second. And learning these features took about 10 minutes. So what we found at the end was that when we looked at the Street View house number data set, we looked at basically a single layer of trained with the k-means, or trained with the supervised convolutional neural network, was giving approximately the same results, or 86% in precision after 20-something epochs, fairly quickly. And that the difference between a fully trained convolutional neural network that would take several hours to train and our technique was just maybe one less than 2% basically, when you use the two layers. So this is clustering learning with two layers, and this is this convolutional neural network with two layers. And we saw that basically convolutional neural networks that are trained supervised with stochastic gradient descent always perform the best on a fixed data set, but even clustering learning techniques come really close, even when they implemented with small networks of 16 filters and 64 filters. We found a similar result on the CFAR data set. Basically, the first layer was about the same, if not clustering learning slightly bigger, slightly better. There was a big difference though in that peak performance with two layers, where a convolutional neural network reached approximately 70%, while clustering learning would reach about 60, not much more. This is because CFAR is a much more complicated data set that requires numerical optimization. We also did some tests on by using this in a robotic application with a dynamic data set. So we used the TLD data set, which is the data set of tracking an object in a scene, we obtained the following results. Basically, when we used the convolutional neural network, it was trained, very large convolutional neural network was trained by Clément Farabet, to be supervised trained on a very large data set of street scene, was always performing worse or equal to a clustering learning technique that was basically used for the same task. And for this task, basically, we had a video that we needed to track a specific object in a video based on just one appearance, and we didn't really have a data set really. So this basically proves the clustering learning is a good technique to do robotic vision systems, and that it can be used even with a small number of filters and in real time.